So in this video we will be looking at simple linear regression from an adequacy point of view. We're interested in finding out if our model rests on a valid foundation. That is, are the assumptions on which the model is based, are they fulfilled? And what are the assumptions? Well, we assume that the random variation in the data exhibits what we call homoscedasticity. And we translate, because the residuals in the model is our best measure of the random variation in the experiment. We translate that into residual homoscedasticity. And what is a residual? Let's just recap that. The residual is you could call it the error, the difference between what the model predicts and what we actually observed. So these vertical distances represent the residuals, and we have as many residuals as we have observations. And the residuals, the variance in the residuals is our best measure of the variance in the data, in the y data. And because we assume that there is a homoscedasticity in the variance, then we must explore whether there is a residual homoscedasticity. And what does this mean, this terrible word? Well, what it means is that there should be no pattern in the numerical value of the residuals. That means it shouldn't be like we have small numerical residuals in this end of the plot and then large ones over here, or maybe large in the middle and small ones on either side. It should be more randomly distributed, and there should be no obvious pattern. That's basically what it means. How do we test that? Well, the typical way is to make a residual plot, or rather plots, because we can plot the residuals as a function of the x values, or we can plot the residuals as a function of the modeled y values. And what we expect to find is that the residuals distribute themselves on either side of this axis here, and not just that, but that they have there's no pattern in this plot either. There shouldn't be like a pattern. And maybe it's easier to see something that's not homoscedastic. Just a minute. So here we see an example of residuals that are homoscedastic. So they distribute themselves randomly around this line here, the x-axis. There's no pattern, whereas in these two cases we can clearly see that we have larger residuals, numerically larger residuals over here than we have in the middle. So we have like a bow tie or a butterfly shape, and here we have a fan or a funnel shaped, some people call it a trumpet shaped pattern. Both of these are heteroscedastic, and that's not what we want to see, because our assumption on which our regression relies is that we have homoscedasticity. The other assumption that we have is that there's a normality, that the variance in the y values is normally distributed. What does that mean? Well, that means that we should have most of the residuals close to the line, just like a normal distribution. So we could actually, let me find another color here. I'll use this one. So we could draw like small normal distributions. I'm not so good at that. Shoot, that was a bad one. Like that. So we expect most of the residuals to be close to the line, fewer further away, and very few far away. That's roughly what we mean by a normal distribution. And if we go back to look at the picture from before, if you look at this homoscedastic plot here, it seems like that could be a normal distribution. We have many residuals close to the line, that is zero, close to zero, and fewer further away. But that's hard to tell from this plot, so we need to make another kind of plot, and that's the, not surprisingly, the normal plot of the residuals. Sometimes it's called the QQ plot. That's a more general term. And what that is, I'll just change the color here. The normal plot is a plot in which we put the residuals on the x-axis, and then we put a normal score on the y-axis. The normal score is a number that we compute, which basically tells us what number we would expect if the residuals have a normal distribution. So we sort of compare those two samples, the sample of the residuals, the sample of normal scores, and what we expect to find is something that points on more or less a line that goes through the origin. If that's what we find, that means we have a normal distribution of the residuals. If we see something like, and I can find another example, just a minute, something like this, there's an example of something that's not normally distributed, and that's because it does not follow, there's a clear pattern and it's not a linear one. This is fine, this is normally distributed, this is not. So let's try to do this in Excel, and I'll choose the example from before with the pH levels and the yields. Here we have the regression that we did in a previous video, but this time we'll do it a more thorough analysis. So I'll go into data and choose data analysis and regression, and the Y area, they've already been selected, but the Y values are the blue ones here, and the X values are the pH values here. And I'd like the thing to be displayed here, the output, and I choose to see the residuals this time. So let's click OK and see what's going on. So here we have the output. Now we're not going to be talking much about these numbers. We'll save that for another video. But you can see that we have here the intercept and the slope. So these are the two regression coefficients that you recognize from the plot over here. And we also have the R squared value here. Right. But more importantly, in this respect, we have the residuals here. So here we have that's the observation number, 1, 2, 3 up to, we have 20 observations. This is our model response. So these values are the computed values corresponding to the points here on the line here. So that's our model response. And these are the residuals. They correspond to the difference between the observed value and the model value. So they correspond to those red lines here, positive and negative. So now I want to make a residual plot. So what I'll do is I'll choose insert, and I'll choose diagram, and I'll choose the scatter plot here. I don't want that, so I'll select data, and I'll remove those series, and I'll define my own. The x values of my residual plot, well, I'll choose the x values over here, the pH values here, and the y values should be the residuals. I hope I can select them here. Oh shoot, I can't see. Just a minute. I have to move this away here, and here we go again. X values, like that. The y values are the residuals, like that. And let's look at it. And this looks fine, I would say. It's always hard to determine the randomness when you don't have that many points, but there's no reason to be worried here, I would say. So if I could give it a title, I'd say this was the residuals versus the x values, the pH values, and there's homoscedasticity here. And we could do another plot in which we insert scatter plot here. And where did that go? It didn't go anywhere. This is not really working for me. Like that. Oh, there it is. And I'll select the data. This time for the x values, I'll choose the modeled response here. And for the y values, I'll choose the residuals. So it's exactly the same as before, except that the x values are now the modeled response. So residuals versus modeled response, or y hat is the notation the book uses. And again, we see this looks homoscedastic. No reason to worry here. And then we want to make a normal plot of the residuals. So first thing we have to do is to take a copy of the residuals, because we need to sort them over here. And I'll mark these, right click and choose sort, starting with the least one first. Excel suggests that I expand my selection, but I don't want to do that. I just want to sort this column here. So what we have here is our residuals, starting with the smallest one and ending with the last one. And we could call this sorted residuals. I'll zoom in a little bit. And then we want to compute what we could call quantile probability. Basically, what we do now is that we match each of these observations here by a quantile. Since we have 20 observations, that gives us 20 quantiles. And how do we compute the quantile? Well, we take the observation number, we subtract 0.5, that's more or less a convention, and we divide by the number of observations, which is 20 in this case. That gives us the 2.5% quantile. And I'll copy this all the way down here, and then we have all the 20 quantiles in our sample, starting with 2.5%, ending with 97.5%. And we'll convert these quantile probabilities into standard normal quantiles. So I'll take the norm inverse to get the standard normal quantile. I'll give it this probability, choose 0 for the mean and 1 for the standard deviation. So this gives me the corresponding quantile for a 2.5% probability. And I'll make a copy of that all the way down here. You probably recognize this number because we use this quantile quite often when we do hypothesis testing or confidence intervals. What I want to do now is I want to match up these standard normal quantiles with my actual sorted residuals and see how well they match. So I'll insert a plot, a scatter plot. I'll select my data, my X values. In the book they choose the residual, so I'll do that. But that's not, there's no strict convention about that. You can choose them as the Y values or the X values. The book chooses X values, so I'll choose that. And I'll choose the standard normal quantiles as my Y values. OK to that. And what we see here is that the points distribute themselves more or less on a line here going through the origin. So the conclusion would be that the residuals exhibit normality. I write here a normal plot of residuals. They distribute themselves in very much the same way as we would expect something that's standard normally distributed does. And we see that because they are on a line, so the two samples sort of pair up quite nicely. So if we resume to our original slide here, we can say that we've checked the homoscedasticity assumption and the normal assumption, and both of them turned out to be fulfilled.